Hello. Today I'm going to go over the omega and log n lower bound for element distinctness. For some input of size n, there should be at least n factorial outcomes, and we'll use a comparison decision tree. Let's visualize this decision tree. At each node, we are given the indices for the values that we are comparing, and the edges leaving each node are comparative operations, so less than, equal to, and greater than. Let's say we have an input of size 3, and the values are 1, 3, and 2. So in the first case, let's compare x1 with x2. So 1 is less than 3. We go down this left edge onto the next node. And next, let's compare x2 and x3. And 3 is greater than 2. So let's go down the greater than edge, and then we are comparing x1 and x3, and 1 is less than 2. So we have 1, 3, 2 as our accept. And we accept this because we only went down less than or greater than. We did not go down any less than or equals to, equals, or greater than or equals to. And yeah, that's how we know it's element distinctness, because there were no equal values, there were no duplicates. Reject cases would have traversed down the tree with one of the equal cases. As far as the number of edges extending from non-leaf nodes, if we are using less than, equal to, or greater than, then that means that there are 3 edges out of every node, and the height of this tree would be the longest path traversed. And in this execution, it was 1, 2, 3, so the height or the depth is 3. So 3 to the 3 is 27. Now, the size of the input is 3, and 3 factorial is 3 times 2 times 1 equals 6. And 27 outcomes is greater than or equal to 6. So we know that we have at least more than n factorial outcomes. The comparison decision tree would be n log n runtime. And we can make this solution tractable by limiting instances to within a cube. So let's look at this cube from a 2-dimensional perspective. A cube is a convex object, and convexity means that there is some line connecting from x to y all the way through this region. So no matter what, we can go all the way through this region in a connected straight line. For something like a donut, for example, if we go through, there is a part of this line that's not in the region R. So this would be X and Y, and that's not in R. So a donut is no good. And a cube is a perfect example of a convex object. let's define x as our input, and let's say that y is an alternate permutation of input x. So alternate of x. So let's say x is 1, 2, 3, then y would be 3, 2, 1. And these are different by their ordering, but they're both element distinct, and they would both end up in except leaves. Now, this line where y equals x or x equals y is not good, because that would mean that they both end up in the same leaf, the same except leaf, and this is not possible because of the way that we visualize the relational operator traversal. It's not possible for us to put these inputs into a tree and end up in the same path. So this outcome where they end up in the same leaf is a no can do. So this line would be the only part of this cube that we remove as a reject instance, and the rest of this cube from the bottom slice to the top slice would all be except, where x and y are in different leaves. And we can visualize this cube in 3-dimension as well. If it's in 3D, then it would just be something like the wedge was cut out from here. So we removed the reject instance, which would be, we ripped this out, this reject plane, and the rest is except. Okay, so that's the cube in 3D. So to prove that x and y end up in different leaves, we use a notion of z, which is lambda x plus 1 minus lambda y. And z rests somewhere on the line between x and y, because at lambda equals 0, z equals y. And at lambda equals 1, z equals x. So that means that always z is somewhere on this line. For example, if lambda equals 0.5, then it would be 0.5x plus 0.5y, and z would be the midpoint. So z is somewhere on line x and y. So let's consider some indices I and j where xi is less than xj, but yi is greater than yj. And let's say that they both somehow, in this hypothetical case, end up in the same except leaf. And y is still an alternate permutation of x. And in our example of 1, 2, 3, and 3, 2, 1, x1 is less than x3, whilst x3 is greater than x1. So we have this condition. But then if we use z, which is lambda x plus 1 minus lambda y, then say, for example, we subtract these indiced values. So we would have lambda xi plus 1 minus lambda yi equals lambda xj plus lambda, 1 minus lambda, 1 minus lambda yj. And as you can see, if we subtract these, as they are the same elements but in a different permutation, as y is just a permutation of x, then when we subtract this, we have the same value after our subtraction. That would mean that zi equals zj. And if we have an element that repeats, then this should be a reject for element distinctness. So how is it possible then in this hypothetical that x and y end up in except the same except, but z, which rests on the line between x and y, z rests somewhere on this line, how is z in a reject and has some repeating number? So the only explanation is that x and y, which is an alternate permutation of x, must both reach separate except leaves.